Now, let's talk about another quantity which is related to strain energy. So it's strain energy per unit volume, in which we take the U, the strain energy, divide by volume, which is the volume of the specimen that we have here. Again, we are going to restrict our discussion to be any kind of stress that we apply within the proportionality limit. We are not going to talk about anything that goes beyond the proportionality limit. Those are considered out of syllabus because the area are difficult to be determined. Okay, again, within the proportionality limit, the area under the graph can easily be determined. As we've mentioned earlier, this simple right angle triangle here can be obtained using just half multiplied by x, f multiplied by delta L, as what being mentioned over here. Okay, but what I'm going to do is I'm going to modify this equation. I'm going to modify it. I know that this force here is related to stress, and I know that this change of length here, or this elongation here, is related to strain. So I'm going to modify it and re-represent this equation in terms of stress and strain. So I know that if I take my equation, sigma is equals to F over A, I can shift things around and say that F is equals to sigma A. So stress multiplied by area is the same thing as the force being applied. Whereas we know that the strain is equivalent to the change in length divided by the original length. So if we flip things around, then the elongation here, it's basically just the strain multiplied by the original length, which we can put it in here as well. Now, if we regroup the terms, we regroup the variables that we have here, we can put the stress and strain together, whereas the area and the original length here will be grouped together. Okay, why do I do so? Because this area multiplied by the length over here, if you have a specimen, this will represent the area, this will represent the original length of the specimen. So if you take area multiplied by length, what you are able to get is actually the volume of the specimen, or the initial volume of the specimen. So if you shift this initial volume to the left, now you have your strain energy divided by the volume, which is strain energy per unit volume, the focus of our discussion in this video, which is equals to half sigma epsilon, half stress strain. Well, you see that this structure here is similar to what we see earlier, in which it's actually an area of a right angle triangle. So this is again also an area under the area of a right angle triangle, but this is for stress strain graph. So if you have a stress strain graph over here, and you restrict the discussion to be any stress that is below the proportionality limit, then basically this triangle here represents the strain energy per unit volume. Okay, because it's half multiplied by the y-axis, which is stress, multiplied by the x-axis, which is strain. So this equation here represents strain energy per unit volume. So this area here is actually the strain energy per unit volume. Okay, so conclusion, if you have a force elongation graph, if you discuss anything within the proportionality limit, the area here represents strain energy. Whereas for stress strain graph, if you discuss anything within the proportionality limit, the area under the stress strain curve is a right angle triangle and represent the strain energy per unit volume. For strain energy, the equation is half F multiplied by the half force multiplied by the elongation, whereas for strain energy per unit volume, it's half stress multiplied by strain. Okay, so there are two different quantities that we usually calculate to determine the energy for this kind of tensile test or compressive test, and please be clear which is for which. Okay, so that's it for this video.